Welcome to my channel. In this session we are going to see about central limit theorem. The central limit theorem is very important theorem which is much useful for statistical and probability analysis, and it is fundamental for all the problems which is oriented with probability and statistical one. So what is central limit theorem is nothing but considering a random variable x with mean 0 with of 0 variance, mean of 0 and variance, standard deviation, and we can go for the central limit theorem. So now considering the value according to central limit theorem, so what is the statement states here is when the normal distribution is considered, any distribution which is considered, and if you are going to draw about the distribution means it will look like a normal distribution. Taking on any averages of the same with respect sufficient number of samples of the same, and if it is distributed, then we can say it is normally distributed. So how this can be technically explained is the averages of sufficiently large number of sample size tends to be normally distributed even if the individual values are not normally distributed. So simply to remember, you can say even if it is not normal, the averages is said to be normal. So this is the key mantra of this central limit theorem. Even any distribution is not normal, the average taken of the sample values will be a normal one. So considering this, we are going to take a random variable x which is having a mean value of mu, which may or may not be a Gaussian distributed. Okay, it can be a Gaussian distribution or any distribution, so it may or may not follow a Gaussian distribution, and it has a mean value and a standard deviation. Mean is represented in terms of mu and standard deviation in terms of sigma square. So simply notifying it in equation number 1, x is may or may not equal to, so I am giving a approximation symbol equivalent to Gaussian distribution of the mean comma standard deviation, which is nothing but sigma square. So all those is explained again. X is random variable, GD is Gaussian distribution, mu is the mean, and sigma square is the standard deviation. Here you have to note down this mean is nothing but the actual population mean. So we are going to consider the average, that is we are going to take a mean sample of all the variables or any of the sample value variables from this random variable only, and we are going to average the same, and we are going to equate find out whether this averaged mean will be equivalent to the population mean distribution, which is taken in equation number 1. So from this x random variables, if we are considering some samples, say S1, S2, Sn, with some data points, say 30, and this should be equivalent or more than or equivalent to 30 data points only. That is, the n value should be greater than or equal to 30 only. This is called as the number of data points. So why this specifically 30 will be explained in a few minutes. So these samples are considered to be randomly selected. So if I am going to randomly select these samples, so example S1 to S100, so I am taking some n value, that 100 samples are I am going to consider. Under that we are going to consider data points which is taken from 1 to 30. So approximately 30 value I am going to consider. So from S1 to S100, if I am going to notify this as a random variables, these sample points with data points will be noted as S1 is equivalent to x1, x2, x3 till x30. So here 30 represents nothing but the data points, whereas S1, S2, Sn represents a sample values. So for 100 samples, I am going to consider 30 data points and in that sample space which is randomly distributed. Now calculating the mean of the sample values which is distributed. So we are going to calculate mean taken for this S1 till S100 samples means we'll get the average mean. So how we are going to calculate this is, so we're taking x1, x2, that is for each of the variables whatever is taken in small letters x1, x2, x30. The first value of S1 sampled value is taken as the x1 mean value. For the second one it is x2 bar, that is the second sampled value. So similarly I am going to calculate it for 100 sample values. So 100 mean values is that we are going to get. So when this x1 bar, x2 bar, x3 bar till x100 bar value are taken, this x1 bar, x2 bar, x3 bar till x100 bar is said to be the mean values, that is the average taken for the mean. That is, it is simply we can say it is the average mean value taken for each of the random variables which is distributed. So now considering this average mean value, we are going to plot a histogram. So we are going to draw this distribution. So previously, if the distribution is drawn, any distribution which is considered from the data points is drawn means it will not be normally distributed. But by this central limit theorem, if we are averaging the mean and we are plotting it through a histogram, based on the central limit theorem, the distribution is said to follow a Gaussian distribution. So Gaussian distribution, which is very essential in statistical calculation. So before going to know about these types of Gaussian distribution, you need to know about what are the distributions first. So we are normally we have a normal distribution and we sampling for this statistical distribution is very important. So before going to know about normal distribution, we will study or I'll explain you about the basic concept of a uniform distribution. Actually this normal distribution is very simple distribution, and this normal distribution, it is also called as a uniform distribution. So what is uniform distribution is first explained here. So for these data points you could consider the x-axis and y-axis with uniform distribution ranging from 0 to 1. So for this, if there is a random distribution or the sample points is taken as for each value of 1, the probability of the outputs taken for each of these values will range between 0 and 1 in a uniform fashion. So the probability of the output case will be taken in terms of zeros and ones. So these zeros and ones will be selected in this uniform distribution only. So you could see here this yellow mark is highlighted. One is the 1 value, means if 0 is taken for the same distribution. So you could see here both the values of zeros and ones are equally distributed. So there is the chance of equal probability case occurring for each of the output whatever our probability is being taken. Hence this probability is uniformly, or it is taking an equal probability case of zeros and ones. It is called as uniform distribution. So you could see here from 0 to 1 range, it is taking a value of 0 to 1 only. There is no hike in the or peak point value observed in this distribution. So this type of distribution which is having probability with equal points is called as uniform distribution. So the highlighted dark point shows you it is an uniformly distributed curve. This is one of the curve. Now let us consider the some of example values. So I am going to collect some 25 samples from this uniform distribution, and I am going to show the plot drawn for this in case of how it is occurring as a normal distribution. So when we are taking as a normal distribution curve and plotting the case, the curve will not show a distributed curve. It is not distributed. This is what central limit theorem states. So I am going to take some 25 sample points and I am going to plot this 25. For this 25 sample points, I am going to take a mean value. So for the particular mean value, if I draw the curve in this uniform distribution and calculating the mean of the same and drawing the histogram and plotting the histogram of the same will be a different one. So here we are going to show two cases by calculating mean of this 25 samples, which is shown in the left side diagram. So 0 to 1, how the distribution occurs, and now this is the mean value taken for this first set of 25 samples alone. So that is example as we have taken for S1 sample, x1, x2, x3 till x25. This is x1 will be the mean calculated for the 25 samples alone. So if I draw the histogram looks like this with a single bar alone. There is no distribution. So for a single mean we get a histogram which is not very sufficient enough to show the distribution of the data points. So we have to consider more number of data points and more number of means to be observed. So for this, if 10 more data points or sample values are added, what happens here? So here 35, for 35 data points, what will be the sample mean I am going to calculate. So for each one we will get x1, x2, x3, x till x10 I am going to get. So x bar, x10 bar, that is the average mean we are going to get. So for this, if I draw the histogram, now it quite interesting to note down that the histogram which is with one single bar has now a distribution of the data points shown in a curvy nature. So if more number of means are calculated, we can see here more number of samples to be taken. That is for 30 or 40 or 50, the histogram pictures shows a well distributed curve, that is which shows it is normally distributed. So this is what is explained in the central limit theorem. So you could see here, for more number of samples taken, the curve, the obtained distribution will be a bell shaped curve which is said to be a normal distribution. So this is what a central limit theorem says. So for with example we are going to explain further points. So now we are clear with the uniform distribution. So now considering, so even if the uniform, even with a uniform distribution, you could see here that distribution should be an uniform occurrence at the histogram point of view, but it is not uniform. It is also normally distributed when mean is taken. This is what for normal distribution occurrence. Now considering an exponential distribution curve. So for the same point, if an exponential curve is taken, left side diagram, I am going to consider the same 25 sample points and a mean is taken. So for that also you can see in the histogram point only one mean occurrence is happening. So when one mean occurrence is taken, we can see there is no distribution of the curve. So if I am going to increase the mean value, that is if I am going to increase the sample points so that the average mean value will be increased. So for 15 number of samples, what happens? For 25 number of samples, what happens? So if I am going to increase the data points, we can see here the histogram is clearly getting modified in a bell shaped curve. So that is nothing but which shows it is normally distributed. So normal distribution is nothing but which when drawn as plotted as a histogram for every sample values which we are taken as an experimental input will after any process, that is a probability chance of getting a distributed, it will not be the same of the distribution what is given as an input. So for uniform distribution also we got the normal distribution curve, which is a bell-shaped curve. For this exponential distribution also we have seen and we have plotted the curve for 35 samples, which is occurring a bell-shaped curve. So here you could see here, as the number of sample points, data points increases, the bell-shaped curve is more prominent. So here the value which is to be taken or which is fixed for the central limit theorem, the normal distribution will be better if the sample points or data points is greater than or equal to 30. So here the means taken out of the samples in any of this will be normally distributed, which is a bell-shaped curve. So please do remember, for any distribution it will be after taking an average value of the mean, it will be a normal distribution curve. This is what central limit theorem states. Hence now by central limit theorem the Gaussian distribution is given, which we have given in equation number 1, now becomes x bar is approximately equivalent to Gaussian distribution with respect to mu, which is equivalent to the population mu taken in the equation number 1, and variance which is approximated for the number of sample points whatever we are going to take, that is sigma square by n. So this is what explained in terms of x bar, which is the estimated random variable, that is nothing but the mean which we have estimated for the each of the random variables which is distributed in this population mean. And the variance is nothing but with respect to standard deviation with n samples. So both this with respect to equation number 1, it is said to follow a Gaussian distribution. Now we will consider an example so that it will be better for you to understand the concept of central limit theorem. So I am going to consider a simple experiment of throwing 2 dice, which is a 6-faced dice. So the possible outcomes will be, you know about it, it is starting from 1, 1 to 1, 6 to 2, 1 to 2, 6. So it extends for till 6, 6. So each of the facets for one output we will get 6 in each of the outcomes. So there are 6 possible, 6 possible outcomes, that is 6 cross 6 possible outcomes, which is nothing but 36 possible outcomes. So as per this central limit theorem, so how this can be proven that it has a statistical probability, right? So as per the central limit theorem, we know the number of outcomes will be better, that is if the distribution curve sample points is more than 30, it will give a better distribution. So here the number of sample points we are considering here is 36. Hence it is a good example, so we can proceed with this. So here we consider some samples to show the distribution curve visually. So I am going to show you only some data points from this sample points, not 36 I am not going to consider, some 8 points only I am going to consider to show as an example, so that you can visualize and you can imagine how this could be drawn for more number of sample points. So now machine learning, whatever it is the process we are considering now, this is the backbone for this process of machine learning algorithms also, how the randomness of the data points can be fitted and output can be obtained. So here throwing a 2 dice, it can result in the output of D1 and D2. I am going to consider random variables, that is x, and x bar is nothing but the sample mean. So what is the dice sample here is, I am going to consider here for 1, 1. The output can be 1, 1, 1, 2, 1, 3, 1, 4. You can go for 1, 5, 1, 6 also. I have stopped till 1, 4 and went for 2, 1 to 2, 4. So there are 8 times I have considered the samples. So what will be the average mean here is, it is actually x bar, which is mean value. So throwing of 2 dice is, so here D1, D2, 1 plus 1 divided by 2, it is 1. So 1 plus 2, it is 3, divide by 2, possibility it is 1.5, and 1 plus 3 it is 4, 4 divided by 2 it is 2, and 5 divided by 2 is 2.5. So till last value, that is 2 comma 4, we have arranged 2 plus 4 is 6, 6 divided by 2 is 3. So now table 2 shows the number of occurrences versus the probability of chances for the same table what we have drawn in table 1. So x bar is nothing but I am going to see the range of the outcomes value which is available. So starting value is 1 and the highest value is 3. So for 1 to occurrence value 1.5, 2, 2.5 and 3 I have drawn. So number of occurrences for 1 is 1 time, for 1.5 it is 2, and 2 it is 2 times, 2.5 it is 2 times, and for 3 it is 1 time. So the probability of occurrence is also taken. So here I am not considering for 8 values, I am considering the total 36 value. So 1 out of 36, 2 out of 36. So you can modify the data as such. So now how I am going to plot this histogram is very important. So you can visualize how the central limit theorem plays a major role here. So based on the table 2, I am going to draw the sample mean versus the number of occurrences. Sample mean here is x bar, that is the estimated value which is taken a range of 1 to 3. So I am going to draw. So I am just have given 1, 2, 3, 4, 5. So easily you can visualize the values, and number of occurrences is taken in y-axis and sample mean is taken in x-axis. So here for 1 value we are getting 1, for 1.5 we are getting 2, and 2 value also 2, 2.5 it is 2, and for 3 value it is 1. So when you join this, you could see the shape of the curve what you have obtained is a bell shaped curve. So for, as I said, for the 8 samples itself we have obtained the curve distribution which is normally distributed. So if more number of samples are considered, you could imagine these samples could be normally more distributed, that is it could achieve a bell shaped curve. So this is the obtained value for only that is approximately 5 values. So 5 mean value what we have taken for the samples. When any experiment in the is done, so what is the application actually of central limit theorem is explained. So usually we do a lot of experiments with unknown data which is random in nature. So we do not know about the distributions possessed by the data points whatever is considered, or in simple words we don't know what kind of distribution will it possess. Does the curve does the data points possess, or what distribution does come from the data we have selected. So output is unpredictable in nature. So this is commonly we know about it. So based on that, the central limit theorem, we can say this applications includes to find out various features in any experiments, that includes finding out the we can say t-square test to make confidence intervals whatever we have taken for any experiments, and to make a t-test, and also in making ANOVA tests, etc. So these are some of the applications which is mentioned in engineering perspective, which is nothing but dependent on the probabilistic nature. So this is the more prominent applications of central limit theorem when this is considered to be application oriented for probability and statistics. Hope you understood. Thanks for watching the video. If there is any doubt, please comment it in the comment box. Thank you.